So your folks, your notes look like this. I'm going to go to this one here, which has like pictures and stuff, and we'll fill in the blanks together. So here we go. We're going to be talking first of all about static electricity. Then we're going to talk about current. Static electricity is electricity that's not moving. It's charge that's stuck in one area. And then we're going to say, well, what if we attach it to a conductor and let the charge go flowing along? And the reason we call it current is it's sort of like a river flowing. Anyways, key idea. Static charge is produced by electron transfer. Looks like transfer. Let's try that again. Static charge is produced by electron transfer. You might recall way back at the beginning of the year, Brady, I might have said something like, everything that happens, it's the electrons that we're really interested in most of the time. Now, in the last 50 years, that has changed. In particle accelerators and things, we can muck around with the protons and the neutrons now, but by far the easiest, both for chemical reactions and orbits and shells and all that stuff, when we learned the crisscross rule, but also for electricity, it's not a coincidence that it's called electricity, which comes from the word electron. So, before we start learning about electricity, we should review what an atom is, because you guys had a Christmas break. So I wrote down here, draw the structure of an atom and be sure to show the 3 subatomic particles, the locations, and their charges. So from memory, you guys have a little box there, yeah? See if you can draw just any old atom. Don't try and make it a specific element. But what I want you to think about is where the 3 subatomic particles are and label them with their charge. Take 30 seconds to do that right now. Matt's looking really, really... So I think, Matt, we're going to be looking at something like that for starting out. Okay, what's going to go in the middle? First of all, what do I call that middle section? It begins with the letter N. Okay, nucleus, what's going to go in the middle, Matt? Okay. Charge on P is what? It'd be wonderful if there was an easy way to remember that a proton is what? Oh, are you positive? Okay. Charge on a neutron is what? Got to be fussy. I got to disagree with you there. And it's an easy mistake to make because they both begin with N. But actually a neutron is neutral or nothing, zero. What exists in shells used to be called orbits, and you've noticed some of the videos that I've showed you still call them orbits, and each time I pause the video and I say, actually they're not, because orbits make you think like it's a planet revolving around. It doesn't quite work that way. Anyways, what's on the outside? Electrons, charge on them is? Yes. And of course, I always have to tell the joke, and Adam walks into a bar and says to the bartender, I've lost an electron. The bartender says, are you sure? And the atom says, yes, I'm positive. There's the punchline, because it lost a negative. No? Huh? Something like that. I copied a fancier diagram in my PowerPoint presentation, but if you do a quick sketch, the key idea is this. Which type of particle do you think would be the easiest to remove? Electrons. Yeah. Why? Don't overcomplicate it. You're on the outside. So, electrons, why? On the outside. We now can remove protons and neutrons, but it takes lots of energy and usually huge particle accelerators. And you're going to find electrons, you can literally move electrons with a piece of tape. We're going to do a lab that involves that in a second. Done yawning, or shall I yell again? Oh, never mind. We're good. Okay. So, the electron, I knew I had to fill in the blank for you. The electron, because it is on the outside of the atom. Right? We're going to do a short lab. And I have to show you a little video, but first let me give you the handout. Let me pause my video. So what conclusions can we draw from our little charge lab? Well, the first thing is, There are two types of charge, two flavors of charge, two, you know what, let's call them positive and negative. We could have named them anything. We could have named them black and white. We could have named them up and down. We probably would have named them two opposites because they are opposite from each other. We've chosen, Mason, to name them positive and negative, and I think I told you guys, and if not, I'll repeat myself. Unfortunately, Benjamin Franklin was the one who gave the charges their negative and positive names, and he got them backwards. Which charges are the easiest to move around? It would be nice if he had called electrons positive, because it's much nicer and easier to do math with positive numbers. If I had a time machine, if you asked me to make my list of 5 things that I would change, one of them might be going back in time to Ben Franklin and say, hey, call the electrons positive, please. It just makes the math much nicer. In fact, you're going to see later on when we solve circuitry, we're going to just pretend that it's the positives that are moving because the math is so much nicer. So we have two types of charge, positive and negative. In matter, the positive charges, the protons, are basically fixed in place. Only the negative charges can move. So in the TB tape lab, before we pull quickly, both tapes are neutral. They have equal positives and negatives, so no net charge. And I wrote down here, draw a neutral object. A neutral object doesn't mean it has no charge. Doesn't mean it has no electrons. But if I have 1, 2, 3, 4 electrons and I'm neutral, how many protons must I have? So if I asked you to draw a neutral object, what I'm really looking for is the same number of protons and electrons. You could draw, Matt, 6 and 6. I'll give you full marks for that. If you're feeling particularly artistic, you could draw 15 and 15. I'd growl at you because I'd have to count them all, but I would, and I'd give you full marks for that. You could draw 1 and 1. The only where I'd give you a bit of a frown, if you left it totally blank, I'd say, well, that might mean that you think it has no protons and no electrons. No, it has matter. It has atoms, just equal numbers. So equal numbers of electrons and protons equals, we call that neutral. No net charge, no extra charge. When you pull off the top tape, it takes some of the electrons from the B tape. So the top tape, I turn the page. So the top tape has extra negatives. The bottom tape has extra positives. So I think I started out in my diagram with 4 protons in each, yes? That's what we just kind of did with our imaginary diagram. But when I yank off that top tape now, instead of having 1, 2, 3, 4 electrons, it's got extras. You know what? Let's give it 1, 2, 3 electrons, and this guy only has 1 electron left. We would say the bottom tape is positively charged. The top tape is negatively charged. Is that okay, Christian? So, extra electrons. Oop, not positive, Mr. Dewick. Are you positive? No, I'm negative. Fewer electrons, positively charged. Okay. If you gain electrons, you're going to be negatively charged. If you lose electrons, you're going to be positively charged. Most objects that we use every day have a neutral charge. A pen, a balloon. But it is possible to charge them by rubbing them. Really? Yep. But it's a pretty cool one as well. So, static charge. When electrons build up on a material, it becomes, here's our word of the day, charged. We call this charge static because it's not moving. The word static means unchanging. Okay? Charges build up through, magic word of the day, friction. Need to make this a little larger, don't I? Charges build up through friction. And one easy way to generate friction is to rub materials together. This is why often when you have stuff coming out of the dryer, because as the dryer has been tumbling, the clothes have been rubbing together, this is why often you'll have static cling with clothing coming out of the dryer. What happens when you give someone a shock? That's a transfer of charge. One of you had more charge than the other person, and it turns out your nervous system, Maddie, actually works on electricity. Your body generates a tiny amount of electricity through the nerves, and so when you get a shock, that's more electricity than your nervous system wants, and you feel a jump, you feel a bit of a jolt, you feel a bit of pain. Your nervous system is saying, hey, I wasn't meant to handle this much. What do you think lightning is? Static charge on a very, very large scale. Lightning is the charge building, the static charge building up so much that those like charges, electrons, repel each other so much that finally they'll repel each other enough that they'll jump and they'll no longer be static. They'll generate a current. We'll get to that later. Put your pencils down. When lightning hits a car, people inside are safe. Why? Yeah. That most, sorry Brady, ignorant non-science people will say it's the rubber tires. And here's what I'm going to say to you. Brady, the lightning just jumped several hundred meters from the clouds. Don't you think it could jump that much further to the ground between the car and the ground? It's not the tires. It's not the tires. But we can reason our way there. It turns out, actually, it's the metal of the car, which is very counterintuitive. So, like charges repel. You okay with that? We kind of did that with our lab. Suppose you had a quadrillion electrons on this car that came from the lightning bolt. The electrons want to repel each other. How can they repel each other? Yeah. That's one way. They might go straight through into the ground, but even without that, while they're in the car, how can they repel each other? They're going to gather on the outside of the metal shell of the car. Where is the passenger? On the inside. Kind of like this. Let's continue. So here is the key idea in electricity. Like charges repel. Much like when Cole calls a girl up for a date. Unlike charges attract. And then here's the one that explains why you all found when you ripped that piece of tape off, most of you found that it glommed onto your wrist. It turns out neutral charges are attracted to either positive or negative charges. Why? Why are neutral charges attracted to both? Yeah. So you said neutral charges are attracted because they're neutral. I mean, I'm sorry, but if I phrase it slightly different, it's a good thought. Well, it turns out we have to now go subatomic. So put your pencils down, look up. So here is a balloon. I'm going to rub it on the sweater, and the balloon is going to pick up extra electrons. Now, look to the right. Look at the wall. The wall right now, Brady, is neutral. But watch what happens. Look at the wall when I bring the balloon closer. Look at the wall. Keep looking at the wall. What do you notice is happening to the electrons in the wall? Do you see it? The blue things in the wall? What are they doing? Repelled, which means the edge of the wall becomes slightly, what charge? The left side, yeah, the closest part to the balloon. Even though the wall overall is neutral, there's a fancy word, we have polarized the wall. We have moved some of the electrons away, leaving a net positive section, and that's why neutral objects will be attracted to both. That's what was going on with your hand and the piece of tape. You were neutral, but the piece of tape said, oh, I can push some, I think the top piece of tape was negatively charged, so it pushed some of the electrons further up into your wrist, and it found a net positive section to glom onto. Is that okay? Yeah. That's what's going on there. Okay? If I move the balloon away, the electrons will all spread out because they want to get as far from each other as possible. So normally in a neutral charge, they're spread out evenly. But if I bring a charged object, now if this was a positive balloon, a bunch of electrons would get sucked towards the edge of the wall. And that would give me a net negative section there, because the electrons are the ones that can move around very, very easily. And that's what's going on when you stick a balloon to a wall. If you want to even go more interesting, because this is tough to visualize, here is an electric field of dreams. Say, what? Your job is to see if you can figure out which charges are positive and which charges are negative based on observing the fact that like charges repel, unlike charges attract. So there's a charge right there. Now, I'm going to tell you that arrows point from positive to negative. This charge is negatively charged. You okay with that? Is that another one? Are they attracting each other or repelling each other? Okay? Because like charges repel. Now, I'm going to, instead of making the next charge negative, I'm going to make the next charge positive. So you can see one of those guys is attracting, two are repelling. This one here, negative or positive. This one here, negative. This one here, negative. And this is what's going on at a subatomic level all the time. We just don't notice it, but all the time. I'm going to give you something that's going to probably wow you a little bit. All of you, take your left or right hand, doesn't matter which, and press it down against the table. Are you touching the table? You're not. You have never touched anything in your life. What's happening is the electrons in your hand are getting close enough to the electrons in the table that eventually the electrons in your hand and the electrons in the table are repelling each other, and you feel that as though you're touching, but I'm telling you, if we had a microscope and zoomed in really, really close, there's a gap between your hands and your table. There's a gap between your hands and anything you've ever touched in your life. You've never touched anything in your life. Never have. You think you have, because you've grown up that way. But I'm telling you, right now, there's a microscopic gap between my hand and the desk here because the electrons are repelling each other. Let's add another positive. Okay. I wrote down here class discussion, reading check. We're going to do this together, I think. So I'm going to pause the video. So now we're going to get even more specific. Suppose you have a very hot cup of coffee. What would be more comfortable to drink it out of and hold in your hand? A metal cup or a styrofoam cup? Why metal? Or was that sarcasm? Just an answer? What would be the problem if you had hot coffee in a metal cup? It would burn your hand? What does a styrofoam cup do? Okay. So, metal conducts heat. Styrofoam insulates. We're going to use those two words. It turns out that also applies to electricity. Electricity can conduct. There are conductors and there are insulators. So insulators versus conductors. Insulators prevent the flow of electrons or heat. What are some examples of insulators? One that we use an awful lot in industry is glass. Glass is a very good insulator and easy to make. Ceramics. Plastic. Rubber. That's why electricians wear rubber gloves or plastic gloves. Electrons that are removed from or added to one part of an insulator aren't replaced. So a static charge builds up. Electrons that are removed from or added to one part of an insulator, they aren't replaced, and so you get a buildup of a static charge. And the reason it builds up is because it's an insulator, there's nowhere for those extra electrons to go. They're stuck there, so you're going to get a charge. Conductors allow the flow of electrons or heat. Well, what type of elements conduct electricity? I'm looking for a word that begins with the letter M. Metals. So if you add or remove electrons from one part of a conductor, they're immediately replaced because other electrons can flow in along the conductor from a different source. And so static charge doesn't build up. Wait a minute, Mr. Dewick, I got a shock on a dry day when I touched a metal doorknob. That was because you had built up charge because you're a fairly good insulator. And when you touched the metal was able to transfer those electrons down to the earth, and they jumped. And because the metal was a conductor, it took all the extra electrons off of you. The spark jumped across, and you got a shock because your nerves work on electricity, and they had to deal with more electricity than they wanted. But it's not because the metals were somehow storing static charge. Metals don't store static charge. They transfer it down to the earth, or whatever circuit we set it up in. Which of the following is able to allow the buildup of a static charge? Now the key word here is static. A copper rod or a plastic drinking straw? Yeah. You could add extra electrons and they'd be stuck there because they couldn't go anywhere. If you tried adding extra electrons to a copper rod, they would, as soon as that copper rod touched anything else, they're gone. So I wrote here a drinking straw because it's an insulator. Put your pencils down. So this explains how you get a shock on a cold, dry day after walking across a carpet and touching a metal door. What really happens? Well, as you walk across the carpet, your feet rub, can I start abbreviating electrons with E-? Electrons off the carpet, and they flow into you. They're electrons, they're like charges, so they're going to repel each other. So if they're repelling each other, where would they gather on your human body? What's the furthest away they can get from each other? Really, more generally, on the outside of your skin. Okay? They won't gather on your internal organs. They won't gather on your insides. They're going to gather on the outside of your skin. In fact, that's why what they'll often do, because the furthest they can get away is by going on the ends of the hairs on your skin. That's why you, on a dry, staticky day, you might feel really kind of strange. It's actually because the hairs on your skin are standing straight up because the electrons are repelling each other as far as they can. So if you ever have that dry, staticky feeling, check out the hair on your arm and you'll notice, oh, it's sticking straight up. Kind of weird. Okay? So they gather on your skin. When you touch the metal door, well, metal is a conductor, so now the electrons have a path to go to continue to repel each other. So they jump onto the door. They leap onto the door, and you get an ouch. John Travoltage. Okay? So here's John Travoltage. He's going to rub his foot on the carpet. He's going to build up electrons. Now, if we make this distance bigger, he can build up more electrons, and they don't yet have enough energy to make the jump. So he can get really, really charged. And then as we get closer, okay, that one would have really hurt. If we start right here and the electrons only have a short distance to jump, very few charges build up and they're able to jump the gap. Okay? So this is why if you've walked on a dry day across a big room and built up a lot of charge before you touch that metal door, the spark might jump like quite far. Whereas, I have a ski jacket, for example, and I know on a dry day, every time I take it off, it builds up a charge on me. And so I've learned when I take it off back there, I put one hand on my metal filing cabinet, pull my first arm out. See, I'm grounding myself without getting the shock. Then I put my other hand on the filing cabinet, put my other arm out. If I don't do that, as soon as I touch the doorknob, I get a wicked shock every time. So I use science to avoid the shock. And then I also have here electric shock ball, but I brought that out before Christmas. I'll bring it out another time later on as well. So these are all insulators, but they have different levels of, here's our fancy word, electron affinity. It turns out that different insulators suck in electrons at different hungers, at different levels. Well, the fancy word, electron affinity. So we have this chart. You don't have to memorize this chart. I'll give it to you on the test. But we have on the left-hand side a tendency to lose electrons, and on the right-hand side a tendency to gain electrons. So when two objects are rubbed together, the material closer to the left of this will lose electrons and become positive. The materials on the right-hand side will gain electrons and become negative. So what does that mean? Well, looking at this chart, I think I have questions. Yeah. Which would become negative? You guys, did I give you the chart? Stay on the, did I give you these questions or not? I don't think I did. So just stay on the chart. We're going to do this orally. Which would become negative, which would become positive if we rub them together? If I rubbed wool and vinyl, which one will lose electrons? Which one will gain electrons? I'll just put a plus and a minus underneath which ones. Is wool to the right or to the left of vinyl? To the left. So that means it's willing to lose electrons easier, so it'll become positive. The vinyl will become negative. That's actually what I did when I rubbed that piece of plastic was vinyl and the cloth was wool. What about plastic and glass? Let's go see. Here's plastic. Here's glass. So the glass is very willing to lose electrons, which means it'll become positive. The plastic will become negative. This is why, by the way, if you rub a balloon to your hair, not only will it stick very well to the wall, it'll stick great to a window on a cold day as well. It'll stick really well. Or this is why on a dry, staticky day, you may even see the curtains getting sucked in. Okay? What about a balloon and cat's fur? I just have this weird image of them holding a cat upside down while it's squalling for this experiment. I'm sure they did it more disgustingly. They probably killed a cat, skinned it, and used the fur. But anyways, okay. Sorry, which one would become positive? Which one would become negative? The balloon would become negative? You guys seeing how we're figuring that out from the chart? Yeah. So I think on your test, I'll give you a couple of I'll give you this chart. I'll give you a couple of substances, and I'll say if we rub them together, which one would gain electrons, become negative? Which one would lose electrons, become positive? Now, again, remember, it doesn't mean that it loses all of its electrons. It just has fewer electrons than protons, or vice versa. A little bit more, we're going to pause. When you go to the store, actually, you know what? We're going to pause here, I think. So I'm going to go like this.